The next step in our hypothesis test is determining a decision rule. In our hypothesis test, since we are testing the null hypothesis, we will make one of two decisions. We will either reject the null, asserting that we have enough evidence from our test to claim that the null is false, or we can fail to reject, also known as retaining the null, essentially saying that we don't have enough evidence to say that it is false. We are not proving things either way, we are just seeing where the evidence points. In a hypothesis test, keep in mind that we either have enough evidence to claim that the null is false or not false. We are not claiming or proving that the null is true. This sounds like a subtle point, but think of it like a trial. In a trial, the prosecutor is hoping to build enough evidence that the person on trial is guilty, and if they don't build enough evidence, the person is declared not guilty. It is not guilty versus innocent. It is guilty versus not guilty. Similarly, in our hypothesis test, our decision options are reject or fail to reject. It's best to avoid the word accept, if possible, although you will see some texts use accept. While it can be less confusing to say accept the null, it is more correct to say either fail to reject or retain the null. The decision rule specifies exactly when to reject the null hypothesis. For example, how different does a sample mean have to be to indicate that the population of interest from which the sample was drawn is most likely different than the hypothesized population? In other words, when is an outcome, such as a sample mean, considered rare or common? A frequently used decision rule is that an outcome is considered common, so the null is not rejected, when it falls within 1.96 standard deviations above or below the mean, for what we call a two-tailed test, which we'll talk about. We touched on a similar concept back when we said about 95% of the observations in a distribution fall within 2 standard deviations of the mean. To be exact, using the z-distribution, 95% of the observations fall within 1.96 standard deviations from the mean. Extending this to our concept of sampling distributions, 1.96 standard deviations above or below the mean is the area in which 95% of our sample means should fall if the hypothesized distribution was true. The 5% of the time that it falls outside of this area, we will consider the outcome a rare or unlikely occurrence. In these cases, where the sample mean we observed falls outside this area, we will reject the null hypothesis. Using our example, if the sample mean of SAT scores in our local population falls outside the area where the middle 95% of mean should fall if the null were true, then it is considered too rare and we should reject the null hypothesis. Your decision rule is determined by your chosen level of significance, what we refer to as the alpha level. The alpha level is the degree of rarity required of an observed outcome in order to reject the null hypothesis. A common choice that goes with the 95% that we mentioned before is setting alpha to 0.05 or 5%. This indicates that we are rejecting the null when the observed sample mean would have occurred just by chance with a probability of only 0.05 or less if the null were true. In a two-tailed test, this is that area that falls outside of the middle 95% of the distribution. It's important to note that you, as the researcher conducting the test, can choose whatever alpha level that you want. It is an arbitrary choice that is not set in stone, and in certain situations there might be reason to choose an alpha level that is higher or lower, which we'll discuss briefly. Choosing the desired level of significance will depend on how rare we want the outcome to occur by chance alone if the null were true. If we want a more strict rejection criteria, we might decrease the alpha level to 0.01, meaning we only reject at the level where the observed z and corresponding sample mean would have occurred just by chance with a probability of only 0.01 or less if the null hypothesis were true. If we want a less strict criteria, we might increase the alpha level to 0.10, meaning we reject at the level where the observed z and corresponding sample mean would have occurred just by chance with a probability of only 0.10 or less if the null hypothesis were true. The key thing is that it is the researcher's choice. although if the researcher chooses to deviate from the common choice of 0.05, it is worth providing the reason for doing so. Our calculation for the z-statistic is very similar to our calculation for a z-score with a few key differences. Remember, we no longer have single observations that we're working with. We now have a sample mean that we are comparing to a population mean using concepts of the sampling distribution. So our formula for the z-statistic is x bar, our observed sample mean, minus our hypothesized mu, or the population mean value that we're testing, divided by the standard error, which we can calculate by dividing the population standard deviation, or sigma, by the square root of the sample size, or lowercase n. Let's take our previous example looking at the local population of freshmen. We know that our sample mean is 533, and we are testing to see how that compares to our population mean of 500. So the top of our equation would be 533, our sample mean, minus 500, our hypothesized population mean. The bottom of the equation would be the standard deviation of the population, in this case 110, divided by the square root of the sample size, which in this case would be 100. This would get us 33 over 11, which would get us a resulting z-statistic of 3.